Hi there guys, welcome to another video of me, Pedro Marques, founder of Nautical. So you'll have your ML model, language model working on your machine. But what if you could handle a million requests from clients reaching out to your model without crashing it? That's what we're going to tackle today, from architecture to live coding. We'll go from local ML ethics to a scalable monitor service in 5 steps. This is what you have right now. You have your user talking to your local ML model. What's wrong with this? You simply cannot ask all your clients to download the model and run it on their machines. You have to find a way for the clients to easily send an input and your model send back its output back to the client. And the solution for this is for you to use an interface on your computer that can easily receive and output data to the client. Let's call it an API. We'll use an API that I'm going to call it prediction service. However, your machine has a low limit on the amount of clients it can respond to requests. You have to find a way to scale to millions of clients, which you can right now. The solution for it is that you can add a prediction service, which you already have, multiple of them, and then between your user and the prediction service, you can add a load balancer. And on top of, all of this will be running on the cloud, where it can scale indefinitely. Our rule to scale would be that we auto scale based on CPU usage. However, how do you easily replace your current model right now in the prediction service for an improved one? How do you make it easy to store it and the associated metrics to evaluate it? For that, you can use a model registry. The model registry stores the models, the different versions of the ML model that you use to easily load it into the API, in this case, the prediction services. So the API will load the model from it. Load model. You'll need another role, which is the data scientist. The data scientist role will be responsible to register new models to the model registry. Register model. Okay, this is already looking better, but how do you know if the model is working as intended? How do you know if the clients are giving up on the model because it's taking too long to get an answer from it? How do you know if your model is available to your clients right now? Just because the model is up on the prediction service doesn't mean your clients are having a great experience. To solve it, we add another layer called a performance monitoring that is constantly reaching out to the prediction service to check system metrics such as latency and presenting them on an easy format for us to track them on the browser. So let's add them, and then we get metrics from our prediction service. For this demo, we are keeping the API open, but in a real enterprise environment, we'd wrap this in an authentication layer. Since we now understand the pains and the proposed solution, let's move on to the technologies we can use. In terms of technologies, to build the ML API, we'll use the FastAPI. FastAPI is just a Python framework to easily build REST APIs. To build the prediction service, add a load balancer, and run everything inside the cloud, we'll use another technology called Kubernetes, which will handle the scaling based on CPU usage too. For the model registry, we'll use MLFlow. And for the performance monitoring, we'll use Prometheus and Grafana. Let's move on to show what's under the hood with some live coding. Okay, so this is the FastAPI app that we currently have right now. We have an app folder. Inside the app folder, we have a main.py. The main.py only has a router, which is the predict router, which is defined inside the routers. At the predict endpoint, we receive a predict request. The predict request is then used as input for our model to predict. In every request, we are loading the model. After we get the predictions, we encapsulate the predictions in a predict response and send them back to the client. Let's see how the load model works. So the load model works as follows. So it's inside the predicts service. The load model is basically just us loading a file inside the predict service. And then let's go back to the predict again, and then we see a couple of objects in here. We see the predict request, and then we also see the predict response that we are sending back to the client. What are these? These are just schemas that we use inside our FastAPI. These schemas are important to validate the request and also validate the response that we send back to the client. The predict request is just checking if the client is sending at least one text for us to predict. And then the predict response is a list of predictions. A prediction is made with a sentiment label and a decimal. The sentiment label can be either positive or negative. To see it up and running, let's look at one of the predictions. So I'm sending great and terrible, and then the model is returning positive and negative. But now let's look back at the architecture that we built. We said that the model would load the model from a model registry, in this case MLFlow. To load a model from MLFlow, we just need to do the following things. Import MLFlow, set the MLFlow server we want to reach. We need to tell MLFlow which path to look for the model. So all of this will be replaced by return MLFlow by func load model. What if the MLFlow server is unreachable? What would happen is that our server would be hanging forever without terminating the setup. For that reason, I'm going to add a timeout to the model. I'm going to add a timeout for 30 seconds. And with this, the load model will time out after 30 seconds and the server will get an error and we'll be able to see it. To make this even more robust, I'm going to add a try except so that we get a custom error when the timeout occurs. The message like this, we get that it was caused by the model loads, and we hint that the MLFlow server might not be running at this time. Something that you'll notice is that if we receive a request, we're going to load a model from MLFlow and then use it immediately afterwards. This can increase the latency a lot. For that reason, instead of loading the model, I'm going to get it from a cache inside our server. In this case, FastAPI as state variables that we can use, and add an event on startup to load the model. Like this, at the startup of the application, the model will be loaded, and then when we get to the predict router, it will just use the cached version instead of loading a new model every time, which will decrease the latency a lot. Let's look back again at our architecture. What about the Prometheus Grafana, so the performance monitor? We still have to find a way for the Prometheus to get the metrics from our API. The only thing we need to do is to add a new endpoint to our FastAPI. An endpoint that returns the current API metrics to our performance monitor. For that, we'll use Prometheus FastAPI instrumentator. We'll create an instrumentator. You could leave this open, but to make the metrics endpoint more efficient, I'm going to group by the status code, and also I'm going to ignore metrics from the metric service and the endpoints regarding the documentation. After that, I'm going to define which metrics I want to track from my endpoints. So I'll just do instrumentator.add and then the metrics I want to track. In my case, I want to track the request size, the response size, latency, and the number of requests. And finally is to expose the metrics endpoint to the FastAPI. With all of this done, let's kill our current server and run it again. As you can see here, the model is loading only once at startup. Let's try our predicts again. And now let's go to the metrics, which is a new endpoint that we'll use later for the performance monitoring to be able to see those on our browser. We already have the total number of requests, in this case 1, and it was a successful one, which was the one that we just created. You can also track other metrics. In a real-world scenario, you'll also track for prediction drift. So with that, we finish the live coding. Now let's move on to the Kubernetes part, the deployment, and start breaking things to test for scalability. On my project, I have this folder, which is called Kubernetes, where I have the predictions.yaml and another YAML file. This is where I specified all the Kubernetes components and configurations that I'm using. To deploy all of this, I'm going to use this command. Since I already did this, everything appears unchanged and configured. I need to do a port binding on the prediction service that I have on Kubernetes to my local machine. With that, I'm going to show you the dashboard. This is the dashboard of the predictions app. As you can see here, we can check the number of requests per second. And then in here, you can see how many replicas the service has currently running. Now, let's break it. We can do that by to list how many units are we running right now. So what I'll do is delete this unit that is currently running. It's deleting the unit. And as you can see here, I just deleted the unit, but it's already running a new one. We're going to really put the test of scaling. We're going to start spamming the service. For that, I'm going to use another command. This time, I'm going to send 100,000 requests to my endpoint to be able to see the number of replicas scale. And we can already see this scaling. So the API per request per second is in 67. The number of replicas, it's already in 3. All that this so it's already in the 6. But as you can see, all that this shows is that Kubernetes is able to scale our API to be able to handle as many requests as we can. You can check all the code that I've built for this project in the description of the video, where I share the repo code link. So you can just kind of see that full example of an ML API with scaling, self-healing, and monitoring. This is an intro, but hopefully something that you can really use to deploy ML models, because you can push all of this to a cloud vendor. So I'm really hoping you can see the value in terms of big picture. Again, just a quick recap of what we've done. You can run an interface on your computer so they can easily receive and output data to the client with an API, in this case written with FastAPI. You can run a prediction server, add a load balancer, and run everything in the cloud where it can scale indefinitely with Kubernetes. You can use a model registry that stores and versions your ML models to easily load into your API with MLFlow. You can track the user experience metrics with the performance monitoring, such as Grafana and Prometheus. You can fork the repo, try it yourself, and let me know in the comments what you'd add. So again, thank you so much for watching, and I'll see you in the next video. Bye.